All right, so this is going to be the second part of the continuous time Markov chains. And in this tutorial, we shall consider stationary and limiting distributions with some solved examples, okay? So let's begin with stationary and limiting distributions. So I have already explained in our previous tutorial on discrete time Markov chains that stationary and limiting distributions are similar in the sense that they have the same goal or objective, okay? That is, we want to find out if the proportion of times that the Markov chain spends in each state will exist in the long run, okay? However, if you take a look at the expression of limiting distribution and that of stationary distribution, they are different, okay? For instance, if you consider the expression of stationary distribution as defined in equation 1, you realize that in here we want to find out if the proportion of times that the Markov chain spends in each state is the same when the proportion of times is multiplied by the transition matrix. On the other hand, for limiting distribution as defined in equation 2, we wish to take the limit of the transition matrix as time approaches infinity, okay? So let this process be a continuous time Markov chain with transition matrix and state space. A probability distribution given by pi, which is a vector of probabilities on the state space, where pi belongs to a closed interval from 0 to 1, the sum of the element of pi is 1, is said to be a stationary distribution for the continuous time Markov chain if we can define it as expressed in equation 1. So alternatively, the probability distribution is called the limiting distribution of the continuous time Markov chain if the proportion of time that the Markov chain spends in each state can be obtained by taking the limit of the transition matrix as time approaches infinity. So in the case where we have the expression of equation 2, then we prefer to use the term limiting instead of stationary distribution, okay? All right. So for ergodic chains, there exists a unique stationary distribution which will be equal to the limiting distribution. Now, in case you have skipped ergodic Markov chains, you can check it out by clicking on the link in the card above or check the description below this video for the link, okay? All right. Also take note that finding the transition matrix of the continuous time Markov chain is very difficult. So due to this, there is an alternative way to obtain the limiting distribution of the continuous time Markov chain from the limiting distribution of the corresponding jump chain, okay? So let's consider this theorem. Let this process be a continuous time Markov chain with an irreducible positive recurrent jump chain. Now we know that having an irreducible positive recurrent jump chain is the same as an ergodic chain, okay? Now take note that for continuous time chains, we don't need to worry about periodicity or aperiodic state because times could take any positive real values and will not be multiples of a specific period. So having an aperiodic state, which is a positive recurrent, will give us an ergodic state. In other words, having an irreducible positive recurrent jump chain is the same as an ergodic Markov chain, okay? So suppose that the unique stationary distribution of the jump chain is given by equation 3, so this is pi hat, such that we can also have this expression. Then the limiting distribution of the continuous time Markov chain can be obtained by using the expression in equation 4 for all states I and j, where pi, which is a vector of probabilities, is the limiting distribution of the continuous time Markov chain, and lambda index k is the transition rate for each state, okay? So let's take a look at an example. Consider a continuous time Markov chain with two states. We have state 0 and state 1. Assuming holding parameters are given by lambda naught, which is equal to lambda 1, which is equal to lambda. That is the time that the chain spends in each state before going to the other state has an exponential distribution with parameter lambda. So we want to find the stationary distribution for this chain, okay? Now we have already seen this example from our previous tutorial. So let's take a look at the solution. So from our previous tutorial, we obtained a transition matrix in this form, okay? So in case you have skipped that video, you can check it out by clicking on the link in the card above or check the description below this video for the link, okay? All right, so we want to find the stationary distribution. So let pi be equal to pi naught, which is pi naught and pi 1, okay? It's going to be a vector of probabilities. such that if you have to sum this 2, it should be equal to 1. And you can also have this expression. So we can rewrite equation 6 in this form, right? So we want to solve equation 5 and 7 simultaneously. All right, so this is basically what you're going to do. We'll pick this vector and multiply by the first column here and equate it to pi naught. Then you also pick this vector, multiply by the second column and equate it to pi 1, okay? So this is basically what you're going to obtain. All right, so once you group like things, you're going to have this. And if you try to factorize out common elements out, you're going to obtain this. So once you work out, you are going to have pi 1 to be the same as pi naught. So we want to substitute equation 8 into equation 5, and there's going to be a result. Okay, so we have pi naught to be half. Now from equation 8, we have pi naught to be the same as pi 1, so this will also give us 1 out of 2. So this means that the proportion of times that the Markov chain will visit either state 0 or state 1 as time approaches infinity is approximately 50%. Okay. All right, so let's take a look at another example. Consider a continuous time Markov chain that has the jump chain shown in figure 1. Okay, so this is the state transition diagram that we're going to make use of. So assuming holding parameters are given by lambda 1 to be 2, lambda 2 to be 1, and lambda 3 to be 3, we want to find the limiting distribution of this continuous time Markov chain. And we have already seen this from our previous tutorial, okay? So let's take a look at the solution. So first, you note that the jump chain is irreducible. Okay, if we take a look at this, you can see that this is irreducible because we have a single communicating class, or we can see that all the states communicate, okay? So in particular, the transition matrix of the jump chain is given by this, okay? So we have this, or we obtain this from this transition diagram, okay? So the next step is to find the stationary distribution for the jump chain, which is given by this expression from equation, is it equation 3? Okay, so, all right, so we can express this in this form. We know that once we sum all these probabilities, it should be equal to 1. So we want to solve equation 9 and 10 simultaneously. So this is basically what you're going to do. We'll pick this vector, multiply by the first column, and equate it to pi 1 hat. And also pick this vector, multiply by the second column, and equate it to pi 2 hat. Then also pick this vector, multiply by the last column, and equate it to pi 3 hat. Okay. So that's basically what you're going to have for equation 11, 12, and 13. Okay. So we want to substitute equation 11 and 13 into equation 10, and this will be the result. So once you work out, you have pi hat 3 to be 2 out of 5. So from equation 13, we know that pi hat 2 is the same as pi hat 3. So this will also give us 2 out of 5. Now from equation 11, we have pi hat 1 to be 1 out of 2 multiplied by pi hat 3. So this will be the result. So this will basically give us the stationary or limiting distribution for the jump chain, okay? So I want to find the limiting distribution of the continuous time Markov chain, and this can be obtained by using the expression from equation 4, okay? So you just have to input the values. So for pi 1, we know that we can use this expression. So our lambda 1 is 2, lambda 2 is 1, and lambda 3 is 3. And we have already obtained pi hat 1, pi hat 2, and pi hat 3. So we just have to input the values, and this will be the result. The same applies for pi 2. So once you input the values, you also get this result. And for pi 3, once you also input the values, you also get this result, okay? So this means that the proportion of time that the Markov chain will visit state 1 as time approaches infinity will be 3 out of 19, for state 2 will be 12 out of 19, and for state 3 will be 4 out of 19 as time approaches infinity, okay? So this will bring us to the end for this session. Please, if you find value in today's tutorial video, don't forget to subscribe if you have not. Thank you for watching.